Swayam Prabha. Digital India. Educated India.
So, let if C is a monotone circuit for click Kn and the approximator for click is not identically 0, then size of C is at least 1 minus L choose 2 by K minus 1 divided by M square into L choose 2 by K minus 1 whole to the power P. Okay. So again, this is just combining the two things. So, okay, so what do we have from lemma 1? So again, either the approximator is identically 0 or this happens. So if the approximator is not identically 0, then we know that it outputs 1 on these many negative test graphs. It means that it is failing on these many negative test graphs. So by lemma 1, number of negative tests on which the approximator fails is at least one minus L choose 2 by K minus 1 whole to the whole into K minus 1 raised to the power n. Okay, and by lemma 4, okay, what we have is the number of negative tests on which the approximator fails. So this is basically where one gate is failing, but the number of negative tests on which the entire approximator will fail is basically the size times this quantity. So, and that is less than or equal to size of C times this quantity over here, which is M square into L choose 2 by K minus 1 whole to the power P times K minus 1 raised to the power n. And now if you just combine these two, you will get that size of C is greater than this. Okay. combining we get the bump. So I am not writing it anymore. Okay. So what have we done so far? Just to summarize, we kind of divided it into two parts. Okay. So one part we saw if the approximator is identically 0, and the other part when approximator is not identically 0. And then in both parts we showed that the size of the circuit that is that is computing click is at least some quantity, right? So now we have to, so now basically it is just setting the parameters right. Okay. So as a corollary of lemma 3 and lemma 5, what we get is, let me call it corollary 6, a monotone circuit for, right, the name of the function click kn has size greater than or equal to what? What should it be? Basically the minimum of the two quantities, right? So we have two cases, and whatever is the minimum, it must be greater than that. So just, I don't have lemma 3 over here right now, you can look at it. So both the terms have a 1 over m factor in their expression. So I can write it as 1 over m square times the minimum of, what was it for from lemma 3? You can just n choose k by right, and here what we have is 1 minus L choose 2 by k minus 1 divided by L choose 2 by k minus 1 whole raised to the power p. Okay, where what is m? So n and k of course are the inputs. What are m, L and p? What is m? Where was m introduced in the entire proof? So m is the upper bound on the number of click indicators, right? So for a approximation, it is the upper bound on the number of click indicators, and to apply the sunflower lemma, we need to have m to be at least this p minus 1 to the power L times L factorial, right? So we will set m to be p minus 1 to the power L times L factorial. This is what we choose our m to be. In fact, this is what it needs to be, because we are applying the sunflower lemma. What about p and L? So they are some parameters, right? And p greater than or equal to 2 and L greater than or equal to 2 are some parameters, right? So why is p greater than 2? So what was p again? So p was the size of a set in the click indicator, and L was p was the number of petals, and L was the size of a set. Okay, so if the set of, if the size of the set is 1, then I mean there is no or, right? I mean it is a single thing. So there is no, I mean it's just a single vertex. You need at least 2 vertex to form a click or not form a click. So therefore L is at least 2, and P also, if there is a single petal, then yeah, we don't need to bother about that. So we can assume P and L are greater than 2. So now what do we set P and L to be? So first of all, okay, setting the parameters. So we set L to be root k, and let's say it is the we need floor or okay. Yeah, so just one more thing here. So yeah, so we are talking about a monotone, we want to, yeah, so we are talking about a monotone circuit of C which has size at least this. So suppose let C be the smallest sized monotone circuit for click. Okay, so we want to argue about the smallest size circuit, that the size of that circuit is greater than something. Okay, so set L to be root k. So if I set L to be root k, then L choose 2 by k minus 1 is what? So what is L choose 2? L is, well, L square minus L by 2. So L square minus L is k minus root k by 2. So this you can show as less than or equal to half actually. So k minus root k divided by k minus 1 is less than or equal to 1. Okay, so this is one part of it. So this is what we get. And what is the other place where L appears? L also appears over here. So let's look at this. So also n minus, or let me actually do the full thing. So n choose k divided by n minus L minus 1 choose k minus L minus 1. What is this? So note that both these terms have a n minus k factorial in the denominator, which cancels out. So actually if you just simplify this, this boils down to n into n minus 1 all the way up to n minus, I think n minus L minus 0, yeah, n minus L, and this will be k minus 1 up to k minus L again, and this can be shown to be strictly less than, I mean each of these n minus I divided by k minus I is actually, it's easy to see that it is less than n by k. So this is n by k whole to the power, the number of terms here are L plus 1, so L plus 1. Okay. So now let's try to simplify this, what we get. So therefore, so as I said, I'll just consider that circuit as C. Size of C is at least 1 over m square. Let me write the full thing. Minimum of, okay, so this is upper bounded by this quantity n by k into to the power L plus 1, and this is 1 minus, so this is lower bounded no, so this is not implying this, right? So actually this should be greater than, here, because if the size is bigger than this, then only if I have a smaller quantity can I say it is bigger than the smaller quantity as well, right? Yeah, so this is what you can prove, that each of these n minus I by k minus I is greater than n by k. Yeah, you can just try that as an exercise. It's checked it out. It's simple. Okay, so this is the thing. Yeah, now it is clear. So L choose 2 by k minus 1 is less than half. So this is greater than half. So 1 minus this is greater than half. So 1 minus of half over here, and in the denominator again we have this. So again half raised to the power p. So this is greater than or equal to again I can substitute for m over here as well. So p minus 1 to the power root k into root k factorial. So root k factorial is upper bounded by root k to the power root k. So I'll write it as root k raised to the power root k, okay, whole square. N by k to the power L plus 1 comma two to the power p minus 1. So again L is nothing but root k. So root k plus 1 is of course bigger than root k. So I can write this as root k. Okay. Now I will, the last thing that I have to set is p. So I will set p to be log n plus 1. Okay. Or I need k. Sorry, I want p to be k, root k log n. Root k log n plus 1. Okay. So again size of C is at least 1 over, so p minus 1 is root k log n into another root k whole to the power 2 root k, k log n actually, times minimum of n by k to the power root k, and this will be n to the power root k. Okay. So among these two quantities, it is easy to see that n by k to the power root k is the minimum. So therefore size of C is greater than, so root k gives me k over here, k log n to the power 2 root k times n to the power root k divided by k to the power root k, right?
is it greater than?
Hmm?
How is this thing becoming greater than?
Which one?
This
This one. So that's what I said. So each of these terms, n minus I divided by k minus I, is greater than n by k.
but it is not working. Like suppose like I take 5 by 10 and I do 4 by 9. So 4 by 9 is not greater than.
No, 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 no. It is for n and k. So n is greater than k. You have to take 10 by 5.
Okay, so 10 by 10.
Yeah. Yeah. So when n is greater than k, then it works. Okay. Anyway, so again, so actually if you just simplify it, I'll just write down the simplified expression. I have it here. So actually n by k cube log square n whole to the power, whole to the power root k. Okay. So now the question is that when does this give us a lower bound of n to the power something. Okay. So now observe that if I take basically, so when is this entire quantity bigger than n? Okay. So note that if I take for k less than n to the power 1/4, this inequality holds. Okay, so if I set k to be less than n to the power 1/4, then n by k cube log square n is greater than or equal to n, which implies that size of C is greater than n to the power root k. And this is the theorem that I stated yesterday. Okay, so just to recall, so this shows that let me rewrite the theorem. There exists epsilon greater than 0 such that for k at most n to the power 1/4, there is no monotone circuit for click kn of size less than n to the power epsilon root k. Okay. So this proves the theorem. Actually, we have 2 to the power epsilon root k, so which is anyway, which is why that epsilon is actually occurring. So yeah. 2 to the power n I can write as 2 to the power log n. Okay. Because I want it to satisfy that this term is bigger than n. This term. Huh? It will actually work for even slightly smaller n. So if you actually look at the equation, when is n by k cube log square n greater than or equal to n, so you will get something like n to the power 1/3 divided by log square n to the power 1/3. You will get something like that, which is anyway bigger than n to the power 1/4. So that's why. So we have this k cube over here, which is where you have that 1/3, and 1/4 is just a safe smaller number. Okay, so basically, so this is just the mathematics. I mean, this if you just work it out, you will kind of see it is nothing. There is no great intuition over here. It is just setting the mathematics correct, but the intuition is actually in the first part. Okay, so where it is basically we are kind of dividing it into two cases when the approximator is 0 and not identically 0, and then what the way that we follow is that if we look at the approximator for click, then the approximator will have size bigger than some quantity, but if I want to approximate each gate, then the approximator makes some small number of errors. Okay. So for the entire click function, the approximator will kind of not work on many inputs, but for each gate it is not working on some small number of inputs. So if I combine these together, then I get that the in order for the approximator to work, it needs to have size bigger than some quantity. Okay, so thank you. So this completes the proof.